Hello and welcome back to class after your Christmas break. In this class, we're going to be looking at automation technology. And it's an amazing world of all sorts of sophisticated integrated circuits and ruggedized systems as people have tried to get the electronics to be able to function in industrial and commercial environments where it's not quite as nice as your home, not as comfortable as your house. But first, let us look at the various elements that we have to deal with. And I'm not going to read out these slides verbatim. I've put a lot of effort into writing the slides, and you can just freeze them in between and transfer the information to your memory or to a piece of paper or whatever you would like to do. But on this first screen, we're comparing the microcontroller to the microprocessor. Now, the microprocessor is a general purpose CPU that interfaces to various peripheral chips or to external memory, or even to hard drives or whatever as required. The microcontroller takes the idea one step further, and it combines the input and output functions directly on the one chip. Therefore, the microcontroller essentially contains a simple microprocessor and the necessary I/O to make it work in a situation where we have sensors and we want to control something like actuators, motors, whatever. So that's the big difference between the microcontroller and the microprocessor. The microprocessor is going to require additional chips and a circuit board and an infrastructure in which to be able to do the control, whereas the microcontroller combines those control aspects into the one chip. The instruction set, therefore, is a simplified instruction set which is primarily intended for input and output control. So the control commands are built right into the instruction set. So therefore you can do what you want to do with a far shorter piece of code than if you had to write the code to do it in the general purpose microprocessor system. So those are the salient points of that. Now, what purpose, task, and objective of the microcontroller do we want to look at? The microcontroller is designed to read sensors and control actuators based on whatever intelligence you program into it. Therefore, the actions that it takes on the control aspect of the thing will depend upon what you want it to do after it's read specific considerations, specific conditions in the sensors. But because it's all on one chip, the complexity is limited to only a small number of inputs and outputs. So for larger systems, we will need the Programmable Logic Controller, or PLC. The PLC does the same sort of thing as the microcontroller. Basically, it monitors inputs and controls outputs. But the difference is that the PLC is part of a bigger system, and this can affect its behavior. For example, the program in the PLC can be overridden or possibly even changed remotely through a network. And the PLC usually has a generic microprocessor system which is expandable to handle far more I/O channels. You can just add additional modules to increase the number of I/O channels, input-output channels. And because it uses the generic microprocessor, it would be capable of more complex and coordinated tasks than the simple microcontroller. So what essentially does a PLC consist of? It has 4 basic modules that can be replaced individually and can be configured for the specific purpose for which you want the PLC. First, there is the power supply unit. Then there is the central processor unit. Nothing unusual here. The interface module, on the other hand, accommodates a certain number of inputs and outputs. And if we want to increase those, we can use a bigger interface module or even several interface modules, because it has the standard address and data bus associated with all microprocessor systems. So expandability is ensured by simply adding additional interface modules. Then it is associated with a communications processor. Remember that I told you that the PLC is used in conjunction with a bigger system where commands are going to be sent to it from a central system through the network, and also you will want to read those inputs at a remote location. The communications processor that's connected to your PLC will depend on its application. If you are using your PLC out in the middle of an oil field to measure and control oil wells or oil pumps, then your communications processor is very likely to be a wireless system. Now, the communications processor will have within it, they might even have a microprocessor subsystem as well to handle the protocol, the wireless protocol that will be used with your wireless communication system. So the communication processor may be intricately related to the actual radio unit itself, the radio transmitter. But if you're using this PLC in a factory situation along with other PLCs on an assembly line, then chances are your communications processor will interface your PLC, your microprocessor of your PLC, to either a copper wire line or a fiber optic cable. So those are your options for use of your PLC with communications. Now, the PLCs, above all else, are designed to be rugged, depending on where they're being used. But typically, they're going to withstand more heat, vibration, chemicals, sand, dirt, etc. And they involve like military-grade electronics chips that are able to handle a wider temperature range, greater noise immunity, and all that sort of stuff is built into your PLC, which makes them rather expensive, even though they look rather simple. A lot of the money is spent in ensuring that the electronics is protected from the environment in which it is going to be used. In the literature, if you're reading on the internet or studying books or looking at other people's videos or notes, the PLC is sometimes called by different names. And we've put down a few of them here. Occasionally it's referred to as an industrial node. On other people may refer to it as a remote telemetry unit. And still others may call it a mobile remote telemetry unit or even a modular remote telemetry unit. Different manufacturers use different names to describe or differentiate their particular product from the others on the market. So you would expect that everybody will not call it by the same name. In addition to being rugged, PLCs may need to be very fast and or handle large amounts of data depending on their deployment, in what context they're being used. Some will need to be faster than others, but if they're being used in a real-time system that's operating on a microsecond system, then you'll need to have a very fast processor or Conversely, it may have a lot of inputs that are sensing a lot of data. This leads to a lot of jargon and acronyms. The field of automation technology, perhaps more so than other electronics fields, is beset with a lot of jargon and acronyms which you need to understand if you're being involved with automation technology. So, what is the difference between a Scada or a DCS system? Well, first you have to understand what those letters mean. So, the DCS just stands for Distributed Control System. That's all it is. A control system that has several nodes spread out over a wide area. Your PLCs will be connected through the networks, one or more networks, to some central control center from which you may issue supervisory control commands and observe the results through data acquisition. So we see that Scada, SCADA, and DCS are intimately tied together. So every Scada system is going to have DCS. Basically, every Scada system is a distributed control system. So by definition, from that point of view, Scada is DCS. But DCS may not always be Scada. The main difference between the Scada system and the DCS system has to do with protocols and interoperability. So therefore, the Scada system is perceived to be, by the majority of people, a greater system than a mere DCS. Your Scada system will typically utilize all sorts of equipment from different manufacturers working together as one big system with appropriate interfaces and protocols to handle the manufacturer-specific details of the system. Whereas typically in the marketing hype, the DCS system will be marketed by one vendor which may or may not be using proprietary protocols and providing proprietary software and or hardware to make it work. So the vendor markets various DCSs. If you have the right arrangement, you can combine maybe several vendors' DCSs into one giant Scada system. Finally, we get to Fpga. What does that stand for? What is it? Well, a field programmable gate array. And it's a very wonderful piece of chip that allows you to configure hardware logic using software. That's the best description, and I made it up just for you. The advantage is you can completely rewire the hardware logic by simply changing the program code and reconfiguring it. This is a lot faster than desoldering and rearranging wires on prototype boards, which could typically have hundreds or even thousands of wires if you're doing a big system. So as you can see, there's a real urge to use Fpga chips instead of standard hardware logic. But why do we want to use hardware logic at all if we have microprocessors? Well, an Fpga fits into the scheme of automation technology because hardwired logic is typically more reliable and the response time is faster than a microprocessor system in certain key applications. Fail-safe systems and timing systems would typically want a hardwired system rather than an adapted or configured microprocessor-based system to achieve these objectives. So we can well use Fpgas in the overall Scada system for those nodes where they are required. and where their speed, their additional speed, will be an advantage. Finally, we need to consider the industrial network on which all of these nodes run. And this is what makes Scada and DCS possible in the first place. And it is the backbone of the modern factory. It can be based on a fiber optic ring or some kind of two-wire bus like the CAN bus. But indeed, without appropriate networking, Scada would be impossible. What can Scada do? It can remotely control multiple factories around the world from one or more central control centers. Industrial networking using a combination of wire, optical fiber, and wireless channels will be considered in the next few months as we dig deeply into the basics of automation technology. And we look at what's available to the system designer, and we share in making some of the decisions and considering some of the constraints that concern the very well-paid Scada systems designer. Thank you for watching, and I look forward to seeing you in the next video.